unmute.
Paul is going to pray. Paul, pray.
Kirungi, we can't hear you. Kirungi, we can't hear you. Please. Ria, let's have Ria pray for us. Ria, please, unmute.
All right, let's humble ourselves for the prayer. Loving and everlasting Father, I want to thank you for the gift of this day. I want to thank you for the gift of life. I want to thank you that you have been able to see this brand new sun. King of glory, as you are going to have this lesson, pray that you may send down your Holy Spirit to be with us and guide us. We thank you for our teachers, and may you be able to guide them in whatever they're going to teach us, so that we may be able to understand. In Jesus' name I pray.
Amen. Yes. Thank you. Thank you. Yeah. So friends, as I said at the start, to have order here, please, we shall require you to mute and only put up your hand if you want to say something. And we said as well that it is very important to rename your devices at least with your first name, because we can't identify you. As say, if you have Infinix Hot, please, we request you to at least rename your device. That is okay. Here's the team, senior 2 and senior 3, and we are here to work out a practical, to experiment a practical online, the first of its kind. And as I said earlier, that we have teachers here to facilitate this. As well, teacher Doreen is on board. So we are going to
Mr. Joseph? Mr. Charles, are you still hearing Mr. Joseph? Mr. Joseph, you can continue. I think we had lost you.
Okay, I had a technical glitch, but I'm back. So I was saying that after we shall require you to graph in your free time. So we expect to be here. We are supposed to start at 10 to noon. So we expect to have all that within the time left in that case. So I request teacher Palas now to take over. He's going to take us through the software we need and what we require in this case. Over to you, teacher Palas.
Thank you very much, Teacher Joseph. Good morning, everyone. Thank you for that good introduction. I kindly request that in case I go off, Mr. Kazira Stephen or Mr. Joseph, you take over. I'm having challenges of internet here. It's on and off, but as of now, I'm on. Dear students, you are welcome to this platform where we're going to do a number of things, as our colleague or your teacher has said. But for me, my part is to take you through these labs, these electronic labs that you can use. And I'll straight away share my screen with you so I can take you through before we start doing the real practical that is intended for us to do today. I don't know whether you're able to see my screen.
Yes, we are.
Okay. Now, I did not tell you how to get here because of time constraints, but if you are using a computer or you are using a smartphone, in your browser, the browser that you use, if you typed in PhET, as you can see on the screen, on my browser, you will be able to see PhET, which is P-H-E-T. PhET is an interactive medium which enables us to help us to study a number of things in science subjects like biology, chemistry, and physics. As you can see on the screen, the subjects, we have physics, which we are going to handle today. We have chemistry, we have math, we have earth science, and then we have biology. So those are some of the things. Now, these simulations can aid us to learn so many concepts of physics, such that they are not abstract to us, that we can see them, we can feel them, and we can exercise them. As you can see here, I have, we are looking at physics. So there are simulations under motion, under sound and waves, under work, energy and power, heat and thermodynamics, quantum phenomenon, this is above you, light and radiations, electricity, magnets, and then circuits. Those are electrical circuits. Now, some of these for higher level of education, maybe senior 5, senior 6. Others are things that you really studied. As I told you, I just wanted to take you through a few of those. Some of these together, as we interact, we'll be in a position to look at each of them, but we don't have that time now. We may look at only 2 or 3, because I have to use a few minutes I did not want to use so many minutes so that we leave time for the actual practical that we are going to conduct. But I'll take you through that simulation we are going to use for conducting a physics practical, which is called the Pendulum Lab. Are you able all to see this one, the Pendulum Lab?
Yes.
Hello?
Yes, we can.
Okay. So now when I click on the Pendulum Lab, it will come on screen. I have a slow machine, so you bear with me. So here it comes. Now, I also want to say this. Students, we can access this. Some of these, like when you look at Pendulum Bob, it can allow you to download it, as you can see, but it is so heavy. It can take you over 1.5 hours if you want to do it. But my experience that I have, that I don't need to download it. I can only come here on my browser and use it. Now, the good thing that once you've opened it, even if power goes off, you can still use it. That would be the fear. Now, this Pendulum Lab can help us to study about predict motion, simple harmonic motion. Simple harmonic motion we only mention it in your classes, Senior 2 and Senior 3. But for the guys that do physics at A level, it's one of their topics. So we shall not dwell on that. You can also look at conservation of energy. That's what we learn. That's between mechanical, which is potential energy. As a pendulum swings, as it oscillates, it changes energy from kinetic to potential energy. That one we can look at. So let's now, to be able to access all of what these labs give, you need to register using your email. So the things that it requires you is your email, your name, your country, and your school. That is, once you have registered, then you have access to all the lab materials that are provided. If you don't register, it may, some of the things like downloading might be difficult for you, or watching the videos may also be difficult for you. So during your free time, you will be able to explore this. Now, let me open the Pendulum Lab. Yes, I will not go through the introduction part of it. I will not go through the energy. Let me go to the lab. It's straight, as you can see on the screen. Using my cursor, I'm clicking on the lab. And then here we are. So here we are. Now, this one is our pendulum. And we have access to a number of tools that can help us in doing this. For example, in the bottom left-hand corner, we have a checkbox. You have this button. It has 3 buttons: a ruler, stopwatch, and then period timer. We'll be basically using the 3, a ruler and a stopwatch. When I click on ruler, a ruler comes. It is here. When you put it here, it will help you to measure the length of this. This one is our pendulum. It helps you to measure the height of the string. It will guide you. Now, as you can see, the actual length is this line in this blue mass here, where they have put mass 1. So this is the ruler in case we need it. In case we want to do the timing, we click in stopwatch. The stopwatch comes on screen. So for timing, you press this arrow and the stopwatch will start reading. If you would like to stop it, click in the same button and it will stop. And probably if that's the time this mass was swinging, it will indicate so. So this one reads 9.10 seconds. Of course, you don't see the time, but this, for example, what we are reading from the screen is 9.10 seconds. If I would like to reset my stopwatch, I click in this curved arrow and it takes me back to 0. Now, on my left, we have other tools. We have a tool called length 1. This helps us to adjust the length of the string. This can be done in 2 ways. You can drag this blue cursor by taking it left, that is I'm decreasing, or I take it right if I'm increasing. Now I want you to note something here. Let me bring our ruler close to where the mass is. Now, if I'm dragging using this blue cursor on this, as I move it, just dragging, it moves steps of 10 centimeters. I'm bringing it to the left. You can see it goes to 70. It goes to 60 centimeters. It goes to 50. It goes to 40. So this one is in intervals of 10 centimeters. But if I want it to go through all the dimensions, then I use the arrows on the extreme ends. For example, if I click this, you can see how it's changing. It changes by 1 centimeter. Now, unfortunately, as you can see, the time here, if we are using, these adjustments, they are calibrated in meters. Yet, most of the time, we will need our calibrations to be in centimeters. As we do the practical, the teacher is going to take us through that, because all our readings as we do this will have to be in centimeters. Then the second thing is the mass. As you can see, the mass here is between 0.1 to 1.5 kilograms. But if we have ever done a practical at school using a pendulum, we use a bob, and that bob has about between 10 to 20 grams. We have bigger ones for doing other experiments, especially in waves, but I'm not going to go to that. But those that we use for this particular experiment are small. So in the case we'd like to adjust the mass we are using on this pendulum, we can still drag here as we take this one. For example, at this point, if from here, this is 0.2 kilograms, which is still a little bit big, but that we can adjust to that. Here we have 0.that, which is about 100 grams, I think, when you multiply this by 1,000. So we can adjust this. Yes, I can see a hand from Daphne.
Teacher, I'm confused, like, which topic are you handling and what are we doing? Because I'm confused about what you're doing.
Thank you, Daphne, for that wonderful question. We are looking at how we can carry out a practical in determining acceleration due to gravity. That is what the practical we are going to do. Now, what I'm handling right now is how we can do this minus using the tools in a lab, how we can use it on a digital system. I don't know whether I've answered your question. Using a digital lab to be able to conduct an experiment of this nature. Daphne, yes, am I clear to you?
Yes, teacher, thank you.
Thank you. So, my dear friends, I was talking about we can adjust this. These others I'll talk about as we go on. Now, let me try to increase the length of our string by dragging. I'll take this to about 80 centimeters. How do we proceed to do this practical? If we are going to do this, I want to take you through, we shall do it, but I want to take you through. So we can swing. When we drag this, then we release it. It swings as you can see. Now, we need to do timing. Now, what is timing here? We've done two things. We've set our mass such that the length of the string is 0.8 meters. That is 80.0 centimeters, if you would like to say that. And swing now, as you change, let me stop it. As you change it here, you can see it's telling us the angle through which you've taken it. When I stop here, that is 20 centimeters. So when I release it, it is going to go between the extreme end on both sides by 20 centimeters. So now if I bring back the stopwatch and we would like to start counting an oscillation, now you can also see at the bottom here, I also have other tools. Right now, in here we have normal and then slow. I would like to take it to normal. Normal is what we expect for this mass to swing, even when we are in a physical lab. But here I can adjust it for the purpose of knowing what an oscillation is. So I put it here, and it's going to move much slower such that we see what we are talking. Now, when the mass is either of the extreme end, like if it is here, I can start counting from here. Then when it swings, goes to the opposite end, then comes back, that would be an oscillation. Let me be able to use an, if I name this one extreme end to be A, and then I name this one to be O, so I can start my timing when, for example, let me allow this to go back. If it is at A, it goes to B, and then comes back to A, that would be a complete oscillation. Now, if it goes to A, at that point, I now start my stopwatch like that. So it's going. When it gets back to A, I say 1. That will be one complete oscillation. When it goes back to A, then I say 2. That will be the second complete oscillation. It goes forth and back. Now that is the third oscillation. If I wanted the 3 oscillations, I stop. Now here it will tell me that the time for this pendulum to swing 3 oscillations is 4.94 seconds. That's what I wanted you to see about these oscillations. So this is where we are. My string is 0.70 meters. The mass I'm using is 1 kilogram, and I've put it in slow. So, but we are not going to cut out when we are using this. When we are using this point, this kind of lab to cut out an experiment, we want it to swing normally. So we expect it to be here normally. So that's how it should be swinging. There the timing goes a little bit fast. But the reason why I put in slow is for us to know what we mean by a complete oscillation. It swings from A, goes to B, then comes back to A, and that is a complete oscillation. Now, what I also wanted to say, let me erase this, is that we will be able, so here, as you can see again in this other button here, it gives us gravity. And it's telling us gravity. Now here, when I scroll here, there are a number of earthly bodies. We have the Earth, our mother planet. We have the Moon. We have Jupiter. We have Planet X, and we can choose ours. But as we've studied in our physics earlier on, is that this particular experiment can help us to calculate what we mean by acceleration due to gravity. So in this particular experiment we are going to carry out in the next hour, will help us to calculate acceleration due to gravity on Earth. That's why this is on Earth. And that's what we're going to do. Now, one more thing. As we oscillate, I've taken 25 degrees. As we let this thing oscillate, I want you to observe one thing. That even if we sat here for 1 full hour, this pendulum bob would be swinging between the two extreme points I had called A and then B without ceasing. Reason is because here the friction force is none. There is no friction at all. So there is nothing that is going to hinder the movement of our pendulum bob. Now, in a physical lab, that is not true. When a pendulum bob is set to swing, for example, you guys at home, you may want to carry out this particular experiment, a physical experiment, where you are going to use a thread made of thread made out of cotton, then or nylon. Then you are going to sit at the veranda, and wind will be blowing. There will be air friction. So eventually, if you release that bob would start swinging. After some time, you are going to find it stand still. The explanation is that the reason why it does not swing forever is because of air resistance. So maybe if I put friction here, let me put it there. You will see that as time goes on, our pendulum bob is not swinging from one point to another. And eventually, because of that air friction, it will stop. This is, it becomes easier to use this lab to be able to explain some of these things. Why isn't it streaming? Why isn't it going to the extreme ends? What's that? Because here there is air friction. It hinders its movement, and eventually it will come stop. But here for demonstration, I have set it here at 0. That's why it goes through those other points. These are some of the tools. So we can study a number of things using this particular lab. But I just wanted to tell you what these labs, electronic labs, can do for us. If you've already studied about kinetic energy, and you've also looked at the simple pendulum, you know that this pendulum have increased the length to 1 meter. That as you swing this pendulum and it goes, there are energy changes that take place. So if I click here in the top right left hand and I put velocity, you can see that there is a green arrow that has come. Let me put it in low, such that you can see it slow motion. You can see as that arrow moves, it's showing you the velocity at which this body. It can't give you a value, but the length of this arrow will tell you when do we have maximum velocity when a simple pendulum is swinging. When do we have the velocity being maximum? Now, this one will be able to take us to, for example, we know that potential energy, if I write potential energy as PE, is given a formula half mv squared, which means that maximum kinetic energy is attained when you have a swing pendulum, when the velocity is highest. So viewing this, if I have 3 points, let me call this one O, And where it ends, I call it A on the left-hand side. And where it ends here, I call it this B. Then as this bob is swinging, we can tell where do we expect maximum velocity to be and where do we expect zero velocity to be. Can I have an answer quickly? I have about 2 minutes to demonstrate this. Somebody willing to give us an answer in what I've talked about, velocity? Students? Yes, Ruth.
Thank you, teacher. So I think the maximum velocity will be at point A as it is going down, and also point B as it is coming back down to O.
Thank you for your answer. Let me get another person. Any other person who has a different idea? Please put up your hand. Any person? As I said, the longer the thread, a green arrow, the bigger the velocity. So can I, Priscilla, you have your hand up. Can we hear from Priscilla? Yeah.
I think maximum velocity is between A and the 0 in between, and from 0 to B.
We have only 3 points, A, O, and A. So where is maximum velocity exhibited? Priscilla. Okay. Let me go to Faith. Faith has been raising her hand for a long time. So Faith, what's your take?
I think the maximum velocity would.
I didn't hear you, Faith. I lost her voice.
I think the maximum velocity would be at point O.
Good. And 0? Let me say this lastly. Thank you. Then, yes, please come. I made an error. This was kinetic energy. And now this is potential energy, which is given as mgh. So let me, my time is up. We've seen that my maximum velocity is at O, and at point B and point A, we have 0 velocity. The arrow goes to 0. It's not seen at all, so there it's velocity. Now here, H, if we draw a straight line here, I don't know whether I can do it. If we draw a straight line here, like this, you can see that the highest height from this green arrow as a point of reference is highest at the extreme ends A and B. So that is the height. Here at O, the height above this line is 0. So we expect maximum height to be at A and B. So as you can see, that maximum kinetic energy is at point O. So at point O, this bob will have, the pendulum will have maximum energy. Now at the extreme end where the height is high and the velocity is 0, so velocity, potential energy at H is maximum, but kinetic energy is 0. Yet here at O, kinetic energy is maximum and potential energy is 0. So quickly, this is what some of the things that we do. Now, I would like to leave this demonstration with you, and then I would like to invite in my colleagues so that they can put in some addition on what we intended to do, because we are going to 11 and we must do the practical. So colleagues, may I invite Mr. Stephen or Mr. Joseph to take on from here. I was not able to go through other labs because of the time constraint. If we do that, time will not be enough. Maybe we shall arrange for some other day for us to be able to do this. Back to you, Stephen. Stephen, are you there?
Okay, thank you, Mr. Palasi. Thank you for the demonstrations there. Maybe before we go to the real practical, yes. I don't know whether the friends here do have some questions, because we shall need to go through the practical within the time. Maybe you can first attend to them before we head there.
Okay, let me receive a question from the students, because they will be doing this at home. Okay, any questions, students? Yes, Ruth?
Thank you, teacher. Teacher, I was requesting that you take us through the energy changes of the pendulum bulb.
Yes. I didn't get you here.
I said that, may you please take us through the energy changes that take place in the pendulum bulb.
Okay, thank you. Somebody's asking, saying that we go through the energy changes that take place as the pendulum bulb swings. As we look at the principle of conservation of energy, but here I'm looking at mechanical energy. You were saying that as the pendulum bulb is swinging from, say, point A, that end, point B here, it is interchanging between kinetic energy and potential energy. As you recall, the formula for kinetic energy, if I use Ke, is given as half times mass times the square of velocity. And then the formula for potential energy, if I use P, it stands for potential energy, is given as mass times acceleration due to gravity, that constant gauge, then times height. Now, as you can see, is that this bulb is moving in a curve from one extreme point here, then it goes like that to one extreme point here. So it's moving from point, let me call this one point P at the extreme end, point Q here, and then to point R. Now, if I can succeed in drawing a straight line moving like this to this side, and then from here to this side, the velocity of this pendulum bulb is changing. So if I come here and I click here, where we have velocity on my screen, the top, bottom, this green arrow on the pendulum bulb is changing. When it's in the middle, it is when we have it longest. As it goes to the extreme end, it becomes shorter until it disappears, which means as the bulb is moving, it has its maximum velocity at point Q. And point P and point R, it has, at point P and point R, it has zero velocity. So going by this, at point P and point R, the kinetic energy here is equal to zero. So we are saying here at point Q is where we have maximum kinetic energy. But even at point P, the kinetic energy here is 0. The reason being that the velocity reduces to 0 at those points. Now, when we come to kinetic energy, this red line I have drawn passing through point P is our point of reference for measuring how high the mass will be from that line. This red line is our point of reference. So we can see that height h is maximum at point P and point R. They are equal, the heights are equal at these extreme ends. So I'm saying that at point R and point P, kinetic energy there, another potential energy there by our formula is maximum. We don't have a value, but we say as it swings from point A to point B, potential energy is maximum at the extreme ends. But at those points, kinetic energy is 0. So we only have, so again at point 2, potential energy is equal to 0. But kinetic energy at point 2 is equal to maximum. Those are the energy changes that I want to take you through. I don't know whether this answers Priscilla's question and others. Yes, Joseph Chijambu, you have a question? Oh, yes, Teacher Joseph.
No, please. It's okay. You may proceed if there are any other questions.
Okay, is there any other question? Do you think, Teacher Joseph, the time would be enough to be practical and then go through all this? Do we have enough time?
Okay, I think we can head right away because I don't seem to see any other questions here.
Okay. Let me erase this. Is there anything you felt I should have mentioned that I have not done so? Teacher Joseph?
Maybe for now, because our focus, because we are just introducing this to our friends here.
Yes.
I think let's first concentrate onto this and see whether they are able to obtain results. Then maybe in the due course, we shall see how we progress.
Okay. Who is handling the next part of this practical bit? Teacher Joseph?
Yes, Mr. Palasi, you can stop sharing.
Yes. Okay. Thank you very much, everyone. Let's turn over to the next teacher for this.
Okay. Our friends. Okay, friends, as we said, we are handling a practical today, a physics practical online, the first of its kind. And Mr. Palas has taken us through the software we need in this case. Today, we are handling a practical and one of the pendulum bobs, because they are a number, and we posted the procedure. We posted the procedures. We'll share here those procedures as we move through them. Mr. Dungu, I request you to give me course rates. I have lost them.
Jose?
Yes, please.
You will have to call Mr. Dungu because it seems he's so engaged in the other seminar, because also Mr. Kazi was trying to get to him, but he was failing via this means. So we first have to call him physically.
Okay. Let me request Teacher Doreen if she's ready to share with us the procedure. Okay. Okay. Please, you can scroll down. Okay. Let me request someone to read for the aim of the practical right away. Okay. Can you please?
In this experiment, you will determine the acceleration due to gravity, g, using a solid of known mass.
Okay, a solid of known mass. Now, for those of you who attended our lesson last time, where we used a battery cell, you can be able to use that as well. In this case, if you want to work it out without using the software here, you can have your long ruler, you can have a string, and then that mass that we used last time, because we knew its mass in that case. But for now, we are going to be using the software we have right here. Okay, Teacher Doreen, let's scroll down.
Teacher, before she goes down.
Yes, Teacher Peter.
I think they should write, they should start noting in their practical reports because yes, an aim is important on the practical report. I think they should write it down the way they should, because here we say in this experiment you will determine, but for them they will write something else. So I guess you should tell them about that also.
Okay. Thank you, Teacher Peter. I understand we are going to try to be a little bit like physical, but within the time we have, I will first request our friends here to check the WhatsApp. And if you're not on WhatsApp, we shall find you adding you, but we posted the procedures there. So I request you to as well be going through them as we discuss as well here. I think that will quicken up our procedures here as well. Okay. Thank you, Teacher Peter, for that. Teacher Doreen, let's proceed. Okay, someone to read for us what we need here. Anyone ready?
Okay. Can I read?
Friends, we shall request you to put up your hand so that we create order here. So I will choose Kerry in this case. Vivian, please, we shall request you to put up your hand.
Apparatus, centimeter rule, 0 to 100 centimeters, string, stopwatch, your phone's stopwatch, and mass of 10 grams.
Okay, we are using a mass. We are using a mass of 20 grams here because we are trying to find a mass that is a little bit similar to the pendulum bulbs we have in our laboratories at school. Okay, but we shall find as we work through this that the scale we have for this practical simulation, it ranges between 100 grams and 1,500 grams. So for here, it might a little bit differ from what we have here, but we wanted to give you a picture of what you need or how you would experiment this at school. If say used a pendulum bulb whose mass is very small in that case. Okay, Teacher Doreen, please. Okay. Now, Teacher Palasi took us through the simulation in that case, and that is what we expect to have in that case. So you have your rule, meter rule, you have a stopwatch, but at school you can use a stop clock. We shall talk about that as well, because the way we record time in that case is different. But you have a meter rule. In that case, you have a string holding that mass, which is labeled L, and then your mass is the one you have in blue there. I hope that is okay. Okay, Teacher Doreen, let's scroll down. Okay, there. Let me request someone to read for us. One. Okay, okay, sir. Okay, let's have Benjamin, please.
The mass M is suspended using a string on a stand in the as in the figure above.
Okay. Proceed.
Click on the link below to start the experiment. Click on the lab icon. Look at the left bottom corner and enable the ruler and the stopwatch to appear on your screen. Look at the right top corner for the length adjustments. Adjust the length of the mass L so that it's equal to 100 centimeters. Move the cursor and displace the mass through a small angle less than. I think the teacher should scroll down.
Scroll down. Okay, no. Just above. Okay, there.
Move the cursor and displace the mass M through a small angle, in brackets less than 20 degrees, about the vertical, and release it to one oscillate in a vertical plane.
Okay. Thank you, Benja. There. Now, remember, friends, we say that you can experiment this using the simulation you have. Teacher Doreen? Okay. As she's reorganizing, we say that you can practice this or experiment this using the FATE lab online, or you can as well download, and we build the links. But in there we have a link. In there, okay, there, right there. Step 3, we have a link in there. Now, when you click on that link, Teacher Doreen, would you please click? Okay, friends, let me hope you're trying out as well on your devices. If you click on that link, then your FATE lab will open up, and it will take you right away to the Pengram.
I can see Vivian is having a question.
Okay. I request Teacher Peter to look out for the questions in the chat, because I might, okay. Let me see.
I'm trying to look out for them, but I'm not seeing any for now in the chat.
Okay, someone is.
FetLab. I think on the phone we are going to use the link in the what? In the practical.
Yes. For
Yeah,
now,
because
let's use the link in the practical. But after this, we shall post the other links to the downloads. But as well, I think teacher has will help us do that if he's on call with us. But if not here, we shall do that after. But for now, let's focus on to using the link which we have in the
procedures.
In the procedures. Okay. Now let's click the intro. Yes, there, right out. Okay. Shall see that it takes us right away to what Teacher Paras was taking us through. Now, Benjamin read procedure number number 7 and said adjust the length of the mass L so that is equal to 100 centimeters. Now remember, we are using a meter rule. It runs from 0 to 100 centimeters. But you might find out that the readings in there are a little bit different because this project or software is not made in Uganda, but following our UNEB setting, we shall measure our length to 1 decimal place in centimeters, okay? Now, let me request Teacher Doreen to drag that ruler close to the mass. Just click on it and drag it close to the mass, then push it such that the 0 mark is at the center there above. Drag it, okay? Then, like I said earlier, that when you look at the scale we have for the mass, Teacher Doreen, come to this scale on your right. Yes, for the mass, you have the mass running from 0.1 kilograms, and that is 100 grams, to 1.5 kilograms, right? If you try to adjust, okay? So for this experiment, we are going to use a small mass, say, of 100 grams. So Teacher Doreen, please drag that cursor to the last point. But remember, friends, we say that if you can't access this, you can as well use your string, your long ruler, and just use the length you can find along there. And then the battery use that time tight, and then try to experiment this. If you have your stopwatch on your device, then it can help as well. Now, we are beginning from 100.0 centimeters. So Teacher Doreen, drag that mass, drag the mass here on the string. No, not really. Okay, we can even do that.
I start
to
from
100
okay.
Below. Yes,
So
like
just
that.
click on the arrows.
Yes, they can click on the arrows, or they can come to the mass. First come to the mass, this one hanging. No, don't adjust, please. Just leave it at the 0 mark. Teacher Doreen. First leave the row at the 0 mark there, okay? So you just need to adjust this mass. Try to show them that you can either push it upwards, click on it. Okay, if that fails, you can use the scale, no problem. First stop, first click the red button here. Red button, yes. There, such that it rests, okay? Now, if you look through that mass, there is that line midway, okay? That will help us determine along the mass which is hanging, the blue one, here below. Yes, there is that line running through. So it helps you determine the length, okay, or it helps you measure the length along that ruler, okay? So try to make sure that that line is along 100 centimeters. Let me hope our friends here are as well trying out using their devices. Using their devices there.
Well, Mr. Kijambu, I think when I try to put it on 100, it goes down. So can I just lift this ruler and then I put it there?
No, please. Remember, we are measuring that. Don't, because we are measuring from that point above.
Okay, okay. It is okay.
Yeah. So you're measuring that length from that point above to midway that mass, okay? So let them try to adjust. But teacher Peter, look out, because I don't have co-host rights, look out for a student here. I don't know whether he's a student or not. With the tubes, please try to manage that person. If possible, you can remove him or her, because we need to concentrate in here. Okay, so after that, the procedures are saying, okay, for now, teacher Doreen, you can drag this roller away, drag the roller a little bit away to the left. Yes. Now they are saying, move the cursor and displace the mass M, so the one we are hanging right now, through a small angle less than 20. So we saw how teacher Palasi displaced the mass in that case. So teacher Doreen, to repeat that, hold that mass, yes, and drag it to the right. Yes, through the angle, a small angle less than 20. Okay, and leave it oscillate.
Okay.
So friends, we expect you to as well experiment this as we are going through it here. Now, how do we measure our oscillations? Teacher Palasi went through this. So let me request someone to take us through how we experiment this or measure our oscillations. Benja, do you want to do that? Or anyone else? Okay, Sanyu?
The angle, or say the distance through which the pendulum bob moves, we can mark them as A and B. And then we set the stopwatch. If it swings from A to B and comes back to A, that's one oscillation. Yeah.
Okay. Thank you, Sanyu. Benjamin, if you, I don't know whether you just left your hand up. I request you to lower it. Now, our friends, yes, teacher Doreen, please mark for me there on your left. Yeah. On your left, mark, not on your left. Okay. Yes. Mark that point as say A. Or you can just stick it on your left, close to the roller, that mark.
I'm trying to get something to use. So this one, I call it C?
No, you can label it as A, just, okay? Now, even when you stop there, okay? So now, friends, we are looking at a point whereby from point C, okay? If our string comes back to that point C, then that will be one oscillation. That will be our oscillation. Teacher Palasi, I don't know whether you're on call, but
No, I'm around. I'm here.
Okay. Help me, because I don't have co-host rights, please help me look out for tubes. Tubes seems to distract our class here. Okay, thank you. So I was saying that when our string comes back to point C, then that is a full oscillation, a complete oscillation. Okay, that is a complete oscillation. Now, even when you don't start your stop clock right away after displacing your mass, you can first leave it to oscillate, get set, and then begin to count your oscillations. Now, we might be having delays here because of network, but let me hope our friends here are demonstrating as well, of trying this out using their devices. Yes, now, if you're set, as we said, you come to your stopwatch, okay? And click. If it is at C, then click start, okay? Then that will be 1, then it comes back to 3, 4, 5, 6. So friends, count for 20 oscillations. We might have delays, but if your network is stable, please, you should be able to count the 20. Then if you're set, then we stop.
I want to give you.
Teacher Doreen, if you counted, then I had some delays. I couldn't follow up.
I thought somebody's counting for us. Can we repeat?
So they are done.
Okay.
Okay. What did you obtain?
Daphne, what did you get?
Daphne?
Teacher, I had a question.
Okay.
Go on, please.
Teacher, I wanted to ask, like when you're doing this practical, like practically not using a phone, is it you who's pushing the pendulum or it's the wind?
It's you to you make sure that you pull that pendulum to your right, but through a small angle which is less than 20. Then after you release it to oscillate. So it's you who set it into oscillation. But you make sure that the angle is very small, less than 20. Okay?
Okay, teacher, thank you.
All right.
Okay, Teacher Doreen, let's
Yes,
hear
please.
from our friends the time they obtained.
Okay.
Let's hear from them.
Somebody who is having the time, you can tell us the time you have obtained for 20 oscillations.
Someone said it was done.
Anybody to raise up the hand so that we know the person who is going to talk? Okay, yes, Jolie. Which time did you get?
That's 6.9.
Okay.
But
Have you got it?
please. Okay, Jody, thank you very much. But remember, here we are using a stop watch. Okay, stop watch. They are different from stop clocks. Okay, for a stopwatch, we give our, or we register our time to 2 decimal places. 2 decimal places. Okay, and for a stop clock we give to 1 decimal place, but that decimal place can either be a 0, that is to say, you can have 36.0, or you can have 36.5. Okay, and you basically use those at school. So you should take note. Now, because here we are using a stopwatch, we shall give our time to 2 decimal places. And that will be 36 point what?
90.
Okay, 90. Now.
Yes, Kigundu, Teacher Joseph is having also the time.
Okay, Benja?
I got 39.68.
Okay. I don't know. I don't know. Did you use this? Were you following it thus?
Yes.
Okay. But as well, friends, I request you to experiment this again in your free time using the app. Because here you might have delays and our oscillations might not be complete because of network, okay? But we are here to take you through how we can obtain results. Then in your free time, you can obtain more, then graph, and so on. Okay. Teacher Doreen, you can stop.
Okay.
Stop. Yes, then bring back your ruler. Bring back your ruler. Yes, to that mark, your 0 mark should be there.
Okay.
Then adjust now. We are heading to
the length.
The mark now. Yes. Now our new length is 90. Okay. 90.0. So you drag it up to 90.
It is there.
Okay. Then you displace it a little bit. Displace it, sorry, the ruler. First drag the ruler away.
First, remove the ruler.
Yes. Then, because they're repeating now the procedures, okay? But remember, you need to first reset your stopwatch. You need
and
to
also
first
you're supposed to remember. Also, they're supposed to remember the angle which they used for the first reading.
But
so at
okay.
first we used 18. Okay.
Okay, we may not be strict to that. We may not be strict to that because what matters is your displacements should be very small. Okay?
Okay, but then, yes. I think I first reset the stopwatch.
Yes, you need to first reset. Our friends here should not. You need to first reset, then displace. Leave your mouse to oscillate. Get set to start. Remember, we are counting from C. When our string comes back to C, then that will be one complete oscillation in that sense. Okay, are we set to start, our friends? Okay, in 1, 2, 3. Okay, we go. 1, 2. So friends, count because we might have delays here and there. So friends, I apologize for the intro that here. I'm sorry, I can't reclaim my host rights because Mr. Dong is here.
Teacher, at 20 you are done.
Okay.
Yes, we are waiting for you to tell us. May I stop the stopwatch? Okay.
What do you have? Okay, if you're through, what do you have? Benjamin, are you giving us the time? Okay, anyone ready?
Anyone ready here?
Friends,
we have Solomon here.
Yes, Benjamin, please mute and proceed.
I got 39.77.
Okay, friends, we shall need to confirm maybe the other friends here what they have obtained, and then we compare. Joseph, what have you obtained?
39.79.
30?
39.79.
Okay. Jemima? Jemima, what have you obtained? Okay, I think it's not on call in here. Okay, 39 point. So let's, Teacher Doreen, let's stop that.
Okay.
And then, okay, now, friends, you have so far obtained two, but remember, please, let's mute, sorry, let's mute. Okay, I was saying we have so far obtained two values, but if you had observed very well our string and the oscillations, the string was oscillating continuously, okay? But remember, in your life, we shall have resistance. And in that case, we can have air resistance if you're in a physical lab. Okay? But now, if you come to our scale on our right here, Teacher Doreen, move your cursor to friction, friction. Where is the friction? Yes. Now, that can help you drag and include some resistance in your experiment. So for that case, we shall include just a little bit of it, kind of air resistance, and we shall drag to the first mark, okay? And when you try to displace now our mass, okay? If you try to displace our mass through an angle, we shall see that because of the resistance, our oscillations now will be reducing, and with the time, our mass will come to rest. Kind of real life experience. Because for the other 2 points we experimented earlier, as if we are working within a vacuum, okay, with no resistance or friction in that case. But with this, your string or your body will oscillate for some time, and after some time it will come to rest in that case. So now, friends, we shall request you, because we want to have this kind of physical experiment, we shall request you to now drag that mark or scale of friction to the first. Remember, for the first 2 points, we are experimenting when as if you're in vacuum. So for our experiments now, because we already know what to do now, we shall take our mark now to the first one, so that we include in some resistance to motion, okay? Then we shall go back and obtain the results very well. Okay? Obtain the results very well. Okay? And stop for a minute.
Please.
First, stop for a minute. And maybe we take some questions before we proceed. If you have any question, please you put up your hand. Okay, let's hear from Benja. Benjamin, do you want to say something? Or you just left your hand up? Okay.
Sorry,
Can you?
Left my hand up. Forgot to.
Teacher, I'm just confirming if the resistance you're talking about here is the air friction that the teacher had talked about earlier.
Yes. Yes.
Okay.
Yes. Okay. Kemigisa, please unmute.
Teacher, what's meant by acceleration due to gravity?
Okay. Acceleration due to gravity. I think now Kemigisa is running through all the procedures in. Okay. Okay. Before I give my view, Teacher Doreen, would you please mute Teacher Palasi? Maybe you forgot the mic.
Okay.
Yes, click on him, then mute. Okay, thank you. Sanyu, please go ahead.
Sorry, I left my hand up.
Okay. I was saying, anyone to define for us acceleration due to gravity before we give our views? Okay. Okay, very fast. Now, whenever you're having anybody, okay, NASA, please unmute.
Acceleration due to gravity. This is the change of velocity with time.
Okay,
Just
thank you,
that.
right?
Just that.
Yes.
Remember, due to gravity, very important, different from just acceleration.
The acceleration due to gravity. This is the change of velocity with time, with the body falling freely under the influence of gravity.
Okay, rate of change of velocity with time for a body moving in a gravitational field. Okay, or that way that you have put up. Okay, Priscilla, do you want to say something?
Yes.
Okay.
Yeah. Acceleration due to gravity is like when our body is falling towards the center of Earth, it experiences a change in its acceleration due to the Earth's gravitational force.
Thank you.
Okay. Joy, lastly,
Chair,
Joy.
I was just requesting that NASA repeats its definition of acceleration due to gravity.
Okay. But NASA, don't forget rate of change. Okay, NASA,
yes.
may
acceleration due to gravity. This is the rate of change of velocity with time for a body falling freely under the influence of gravity.
Okay.
Okay. Thank you very much, NASA Day. Okay, now the experiment, the experiment in particular here that we are experimenting right away is to determine acceleration due to gravity. So basically, if you're having a body in space above Earth's surface, it will be dragged to the surface. And that force dragging, or the force of attraction towards the Earth's surface, is what we call gravity. And it has an acceleration which we call acceleration due to gravity. And it is given as G. Okay? Now for O level, it is a constant. Okay. We take it as 10 meters per second squared for O level. But when you proceed to A level, it will change a little bit to 9.81 for physics and 9.8 for math. And for the experiments we are going to do in here, we shall see that the G we obtain or acceleration due to gravity ranges within there. 10, 9 point something, 9.8, 9.9, okay? There, around there, okay? If you obtain your results very well. Okay, so, okay, thank you, Teacher Doreen. So for O level, it is a constant for any calculations as 10 meters per second squared. Now, we have brought in the concept of friction, which we are going to consider here as air resistance. Now, friends, we are going to redo this experiment for those results. As we run through our experiment, we are first adjusting our mass to 100 centimeters, but we said, remember, the way we record the results here is very important, okay? We said we measure or we record our length in centimeters to 1 decimal place. That's why for procedure 11, you're able to see that we have 90.0, 80.0, okay? And when you convert to meters, what do you get? Someone to tell us, when you convert the centimeters to 1 decimal place in meters, what do you get? How many decimal places do you get? Anyone to give us the answer? Okay, NASA?
Yeah, 3 decimal places.
Okay, how do you get 3 decimal places?
You divide the centimeters out of 100.
Very good. That's very good. Okay. Now, Teacher Dory.
Yes, please.
We have adjusted our mark for friction to the first. Let's now repeat.
Okay.
These results, let's obtain about 3 of them. But our friends here will do that, count for us. We will measure the time as we have been doing. Then, because we have about 20 minutes, after obtaining 3 of them, then we shall proceed. Okay. We are at 100 centimeter. Then this press through an angle. Okay, to C, please maintain a C. Again, drag a little bit. Okay. So our friends, let's start to measure right away there. Okay, friends, you should notify us when you're through, because I'm experiencing some delays here, so I can't measure the time well.
Yes, Ruth, what have you got?
Teacher, I got 38 seconds, 38.66.
Point what?
38.66 seconds.
Okay.
Okay, Jesse. Jesse, what did you get?
I got 38.16 seconds.
Okay, that's good. Now let's proceed now to hope our other friends are obtained results as well. Now let's reset the stopwatch. Okay, reset. Then okay, we drag our ruler there. Then we adjust to 90 centimeters. Adjust to 90 centimeters. Okay. Teacher Doreen, is that 90 already? 90. Okay, there. All right. We drag our ruler away. Then we displace our mass through a very small angle. We raise it, oscillate.
What? Excuse me, teacher.
Yes, please.
Teacher, I'm noticing the way you're measuring. Are you putting the 90 centimeter mark in between the two pendulum bobs, or shouldn't it be under? Because I'm seeing the 90 centimeter mark is in between the pendulum bob. So
it is supposed to be coinciding with this mark here.
Yes, we are measuring the mass midway. Why? Because for anybody, the mass is concentrated at the center. Okay, that's why you are measuring midway. That's why you mark there. Okay, and it will help you measure very well in that case. So you are measuring midway. Yes, please. You're welcome. Okay. Teacher Doreen, we can
I'm seeing
drag
some
away.
hand. Okay.
Okay. Can you guess, please?
Teacher, I have a question. So, okay, when we started, we first measured the time taken for the 20 oscillations, right? But now, what are we exactly doing? Because I'm quite lost.
Okay, Lynette, maybe we are off for some time. We said that initially our air resistance was 0. Okay, if you look at our scale for friction, initially it was at 0. Okay, as if we are working within a vacuum. But remember, in a physical lab, we shall have air resistance. Okay, so we decided to adjust that scale to the first mark. Okay, so that we add in some resistance to at least experiment this as if you're in a physical lab. Okay, so that's what we are trying to do. And we are trying to repeat now the procedures with the friction there. And for our recordings right here, we shall use that, we shall add in a little bit of friction or air resistance to the first mark. Okay, and we see what we shall obtain in that case. So you're working out with some resistance now.
Okay, thank you.
All right, please. Teacher Doreen, please proceed. We have about 14 minutes. We need to obtain more, just 2. If our friends are ready, then we can start the clock. If you started already, that's okay. Hope they're able to count.
Teacher Joseph.
Yes, please.
At first in procedure, I mean on the first value,
Yes.
You had told me to put back the friction on 0. So I think the value which they obtained at first, they obtained that one when there is no friction.
Okay, Teacher Doreen, the point is,
Yes.
and I think our friends here should note, for the subsequent values now we are obtaining, we are adjusting our mark to the first on the scale of friction, okay? So for all our results that we are going to obtain here, our friction should be to the first mark, okay? But since now they are ready to obtain now the other results, then that is okay. If that is okay with them, then we can obtain just one more. We can obtain just time for one more result or length, then we proceed to the table right
Okay.
away. Yes, please.
Can I put on another length or wait for the value?
They must have obtained the value. Let's hear from them because it is already past the expected time. Anyone who obtained the values there? Okay, Jesse.
I got 39. .26.
Okay, thank you. Benjamin?
41.17.
Okay. Let's hear from other friends. What are they doing really? Are they obtaining something? Let's hear from, okay, Jessia say something. Favor, are you able to obtain something? Vivian, do you want to say something? Okay, Lynette, please.
So I got 37 seconds.
Remember, we are using a stopwatch, and you said for a stopwatch we give our time to 2 decimal places. Okay, 2 decimal places, right? But at school we shall be using stop clocks, and we said in that case we give to 1 decimal place, and either that value can be a 0.0 or a 0.5 in that case. Okay, Ruth, Miracle.
Teacher, I got 36.72 seconds.
Maybe when we experiment this, we shall be a little bit exact in that case, but friends, try to record your results in there. Okay. Teacher Doreen, yes, I think let's hear from our friends whether they have any questions before we proceed to that table, to that table there.
I think I still took where now.
Okay. Benjamin, do you have something to say, a question? If you don't have, you can lower your hand, as well as Lynette and Miracle. Jesse, okay. Jesse?
Is it a must that the time has to be accurate?
Not really. This is a practical, okay? But of course we shall have a range of values, okay? We have a range of values.
Yes.
because if say we are trying to approximate to the exact value as 39.88, okay? Then you should be either a little bit below that or a little bit above that. So that's what I'm saying, as I say, for a range of values, okay? You should be close to exact value, but of course you shall have a range of values in that sense.
Okay, thank you.
Okay, Nicole, you're welcome, please. Nicole.
Teacher Kijambu, can I intervene here?
Yes, please.
For example, here on the stop clock, which is still on our screen, it is reading 48.81 seconds. What have you instructed the students record down as time? Are they recording to 1 decimal point or they are recording 2 decimal points? Teacher Joseph? Yes. And Doreen, what have we told the boys and girls?
Yes, we have told them that since you're using a stopwatch, we are going to record for at 2 decimal places, the way they are seeing it here.
Okay.
Yes.
That's good. Have we gone into the way they are going to calculate the period, or the period T and then the square of the period? Have we been able to demonstrate to them how it's going to be done?
Yes,
because
that's
it
what
was part of the instruction. We are supposed to help them out.
We are going to tell them how to do it, just we are getting some values from them.
Okay. Thanks very much.
Teacher Parati, sorry, I was away a little bit, but I'm back. So we had told them that since you're using a stopwatch, we are giving our values to 2 decimal places, but we reminded them as well that at school they'll be using a stop clock and it gives to 1 decimal place.
Okay.
But that can either be a 0.0 or a 0.5 in that case.
Thank you.
Okay. Now, Teacher Doreen,
okay.
I think we are done here. Let's now go to procedure. Okay, run through. Okay, there. Someone to read for us.
Teacher, before we go to the procedure, I have a question.
Okay.
Teacher, when we are doing this in the lab, how shall we be applying friction? I don't know. That's my question.
Okay. Ruth, I said earlier that of course you'll be having air resistance. So that will be your friction in a physical lab. Okay.
That will be air.
So yes. So you don't need to cater for, because you don't need to cater for friction in that case. You just need to experiment this. But because this is virtual, just simulation, we are trying to include some resistance to approximate to reality. Okay?
Okay, thank you, teacher.
All right. Okay, someone to read for us. Someone to read for us. Lynette, do you want to do that? Procedure.
Yes.
Okay, please do.
So should I start from number 9?
Yes, please.
Okay. 9, determine the time T for 20 oscillations using a stopwatch. You can use the one on your phone. 10, find the time T for 1 oscillation. And then calculate the period. Then 11, repeat the above procedures for values of L equal to 90.0, 80.0, 70.0, 60.0, and 50.0 centimeters.
Okay, thank you, Lynette. Now, the one procedure 11 is to guide you through the values you should obtain as per what you have been doing, okay? But for procedure number 9, they want us to to obtain, okay, you obtained the time in that case for 20 oscillations, right? And that time you obtained as say 39.66 for a given length, okay? Is the time you're talking about. Now, your first time you obtained for 100, for a length of 100 centimeters, okay? We need to first obtain its period. But who can define for us period in that case? If you remember the definition for period, someone to define for us period. We looked at it under waves, if you studied the waves. Okay, Sharon?
Period is a number of oscillation.
Pardon?
Pardon, didn't hear you well.
Period is a number of oscillation.
Okay, that's really, okay. Thank you, Sharon. Vivian, do you want to say something?
Yes, me, I think period is the time taken for a complete oscillation.
Very good. Time taken for a complete, underline that, meaning for one complete oscillation, okay? Remember, you have obtained 20 oscillations, okay? You have obtained time for 20 oscillations. Now you need to obtain time for one complete oscillation. What do you do? That will be your period in that case, and it will be capital T. Period is denoted as capital T, and it will equal to small t, the time you obtained for 20 oscillations, small t, divided by the number of oscillations you obtained earlier. Because with that relationship, you can obtain now time for one complete oscillation. Because remember, the oscillations were 20, and the time you obtained for that case was that. Okay, so for the first value, when our length was 100, what did you obtain as time for that oscillation? Anyone who remembers? Let's use a few minutes from now such that we go through this. Anyone who recalls? Jesse and okay. Benja, we are giving, okay. Julie, what did you obtain?
39.79.
Okay, 39.
0.79.
0.79. 0.779. Okay, get that time, divide it by 20. What do you get? Friends, get your calculators, divide that. What do you get? Teacher Palasi? Teacher Palasi, are you on call?
Yes, please, I'm around.
Okay, please. So I request you to guide our friends here as we proceed at that point now.
About calculating the period?
Yes.
Okay, okay, they can submit their answers.
Okay, let's use this time of 39.79, and then we are dividing by 20.
From the calculated value,
yes, please.
You get 1.9895.
Okay.
Is Teacher Doreen there to write that for us? We have
Yes,
one.
please. I'm trying to get some here.
Okay. So we are 39.79 divided by 20, you get 1.989. Now, the recorded answer, what the students should record down, 1.990, because we must write our answer 1.990. Reason being that the measured value, which is 39.79, has been written to 4 significant figures. So even our final answer for the period should also be 4 significant figures, and the 1.990 is 4 significant figures.
Yes, thank you, Teacher Palasi. Yes, our friends here should note that the time we have obtained will help us determine the significant figures we have in the case. If, say, we are using a stop clock and we are having, say, for example, 39.5, then those would be 3 significant figures. If we are using a stop clock and we had 39.5, those will be 3 significant figures. So when we divide by 20, we shall get or give our answer to 3 significant figures in that case. Okay, Teacher Doreen, let's use at most 5 minutes from now. We don't want to stretch a lot.
Yes, please.
Okay, let's proceed to the next page, lastly. Please scroll down. Scroll down.
Maybe Teacher Doreen, you erase that. Use a rubber to erase that, and so that doesn't interfere with the coming work. Okay.
Okay, there. Now, friends, we gave you a clue about how your table should be. So the procedure above, that is 12, is saying record your results in a suitable table, including values of L in meters. That is very important to note. And then T squared. Okay. Remember, our L initially was given. L was given in centimeters. Now, the L you should write in the first column there. Teacher Doreen, please, you can write that. L should be in meters. Meters, and then close the brackets. Then you write your length. Initially, you had 100 centimeters, then you convert them to meters. As our friend, I think it was Benjamin, said that as well. Go to 90.
Teacher Joseph,
yes, please.
I would like to tell Teacher Doreen that the first column for L is in centimeters, but the second one is the one which is in meters. So the first record the column for L under centimeters as given instruction. Then there will be the next column will be for L converted into meters. Thank you.
Okay. Yes, that is to mean that I should write your results in that order. Okay. If you had length in centimeters, then you need to write them in the first column. Then the next column, you convert them to meters. You convert them to meters. Then the next column, you obtained time. Time in seconds, depending on the instrument you used. If you used a stop clock, then it will be to 1 decimal place, but with a point, either 0.0 or 0.5. If you used a stopwatch like us here, you give to 2 decimal places. Then after having your small t column, so you write the time depending on the length as we measured them. Then the next one will be period, which is capital T. Period, capital T, but again, it is in seconds because we obtained the period by dividing the time small t by 20, and 20 didn't have any units. And then lastly, your other column would be t squared, which is period, because they asked you to include that column as well as per procedure 12. And because you are squaring time in seconds, then that will be seconds squared. The units will be seconds squared. Now, for the column of small t, remember we are recording our results to 2 decimal places. And those are 4 significant figures, okay? So in that column, for small t, you should have 4 significant figures, 4 values to 4 significant figures. And the significant figures will determine the decimal places. And this would affect as well the results for capital T, as well as t squared. So for that, for small t, Teacher Doreen, for small t, the results here should be to 4 significant figures. 4 significant figures. And that will affect the column for t squared. As well, they will be to 4 significant figures and t as well. T, 4 significant figures. And then there are 4 significant.
Excuse me.
Excuse me, teacher.
Excuse me, teacher.
Yes, please.
Teacher, I was kind of requesting, like, after the lesson to be sent the recordings on the group, because like I've just arrived and I don't know where we are.
No problem.
Okay.
We shall do that. Okay.
Yeah. Excuse me, teacher.
Yes, please.
Teacher, what is t squared and s squared?
Okay, Daphne, we said T, capital T is a period. Look at our left corner there. We have small t after small t divided by 20. Okay, the time you obtained for 20 oscillations, divide that time by 20, we define the period as time for 1 complete oscillation. Okay, you had time for 20 oscillations, now we want to obtain time for 1 oscillation, so you divide by 20. So, and as well for procedure 12, they're asking you to include t squared. That's why in our last column, we are including t squared in that sense. Now, friends, for a minute, because we want you to experiment this, let's proceed to the last page, Teacher Doreen. Friends, you can take a screenshot of that to guide you as you're working out. Okay, a screenshot there.
So
okay.
you can remove the annotations?
Yes, you can remove them such that we use a minute. We use a minute to discuss lastly the procedures there. Now, after filling your table very well, they want you to plot a graph of t squared. So t squared will be along the vertical. Okay? against L, but L is our length, but that L we are going to be using is in meters, the other second column you obtained. So you have T squared along the vertical, and then L in meters along the horizontal. And here we are using our graphs, okay? You need to have a graph paper or a graph book. You draw your vertical. Teacher Doreen, please sketch for them the vertical, at least. Sketch for them how a vertical looks like. Okay, and then the horizontal. With open-ended arrows. And a title is very important, but the title you get it from that 13th procedure. You just write above a graph of T squared against L, even when you don't include the along the vertical axis. No, you don't. Just write a graph of T squared against L. Now, depending on the values you have for T squared, you will choose a convenient scale. I don't know our friends here, especially in senior 2, whether they have done some bit of graph work, but if not, we shall have a lesson taking them through that, because our time here might not be enough. But for senior 3s, I guess you know how to draw that. So you choose a convenient scale depending on the values you have for your vertical, that is T squared, and your L. And then you plot, depending on the results you have, along the column of T squared, and then L. L is in meters, okay? Then after plotting your results very well, draw a line of best fit. You can, teacher Dwayne, try to give them a dummy of how they can plot their points. They can be random points. You can, on that graph, you can give them random points. Okay, you choose a convenient scale and then label there. So you can indicate random points in the space there along your graph. Okay, maybe you have a point there, a point there, a point there, and there. Okay, you can have those, though there will be a number of points in there, because remember you obtained results from 100 to 50. Then you draw a line of best fit. As I said, some friends here may not be in position to do this, especially the senior 2s, but we shall have a lesson for them to take to understand this very well. But for senior 3s, I guess you know what you are doing. So you draw a line of best fit. A line of best fit in that sense. Okay, thank you, Lynette, in the chat. I request friends here to help the newcomers here as we conclude this. Yes, so that can be your line of best fit in that case. Now, after obtaining the line of best fit, you choose points. You can draw a right-angled triangle, teacher drawing, along the line, accommodating the points. a right-angled triangle accommodating the points. Yes, like that. And where those lines touch the line of best fit will be now your points of interest. Your points of interest as you calculate for slope. Remember, from math, slope is the same as gradient, okay? And if you remember the formula for gradient, which is M, if you have a straight line, which is Y equals a straight line, which is, okay, given a straight line, Y equals mx plus c, where m is the gradient. Gradient is the same as slope. And when you have any straight line, you can look out for 2 points and they can help you obtain a slope. And in that case, there will be the change in the values along y-axis, but along y-axis, which is our vertical, now we have t squared, okay? So then the numerator will consist of a difference between the values along t squared, then over the change in L, or the values along x-axis in that case. So for the numerator, we expect you to have a t squared 1 value, or y2 and y1. But remember, for our vertical, we have a t squared. Yes, that's very good, teacher Doreen. Yes. Now, since your t squared is along the vertical, so we expect you to choose values.
Teacher Joseph and teacher
Yes,
Doreen, I'm
yes,
requesting teacher Doreen also to indicate on that graph where the value for x1 will be, x2, y1 by using the green mark, so that the students will know the value for x1, the value for x2, y1, like that. Thanks very much. You can continue, teacher Joseph.
Okay, thank you, teacher Palasi. Noted there, teacher Doreen. Okay, yes, the dotted lines are very important there. So friends, we shall give you time to screenshot this such that it guides you as you work out final. Okay, so those lines running through the triangular right-angled triangle you drew earlier will help you obtain the points you need for the change in t squared and then change in L in that sense. So those two values or points or coordinates will help you determine the slope or gradient, as we said earlier. And after obtaining gradient, which is our slope, that is procedure 14, then you head to procedure 15, lastly, where we want to obtain G, and G is our aim, which is acceleration due to gravity. So we shall use that formula that teacher Doreen is putting in the box. You know already your S, which is your slope, using the formula we obtained there. Okay, you see your S, which is in the denominator there. You have E equaling to 4 pi squared over S. So you know your S from slope. 4 pi was given there as 3.14. So you will square your pi. Pi times 4 over the slope you have obtained, and then you'll be able to obtain your value of G, which is acceleration due to gravity, but in meters per second squared. The units will be very important. Where do we get the units? From our vertical, where our t squared was s squared, and our horizontal, which was L in meters. So for now, friends, I request you to take a screenshot of that to guide you through as you work out this. As you work out this. And if you're through with that, we shall welcome a few questions, and then we shall close this for today. Any questions, friends? If you have any questions, you put up your hand. Vivian, please mute your mic. If you're not saying anything. If you have any questions, please put up your hand and it will guide you. Okay.
Vivian had raised her hand.
Vivian? Okay, Vivian, I think she has lowered her hand. Any questions, friends? We don't want to extend this for so long. Okay, if there are no questions, please, thank you very much for attending this. It was the first practical of its kind. We thank the friends who have kept here for all this time. We ask you friends to come back again when we arrange for this, but as well make use of the FATE. It has a number of simulations that can ease your work. But profoundly, let me thank the teachers here. Our host, Teacher Ronald Dungu, Teacher Palasi, Teacher Doreen, Teacher Peter, Teacher Stephen, and the rest of the teachers who have been on this call this morning till the afternoon. We thank you very much. So for now, I will say thank you for coming. Let's meet on Monday for other arrangements as per the timetable, but please let's proceed with the chats.
At what time? Which day? At what time?
Okay, we have lessons always on from Monday to Friday at 2 p.m. to 4 p.m. Okay. Yes. So look out for our WhatsApp groups. If the groups are full, then we are going to.
Can you send us your contacts?
Other groups. Okay.
Don't have the group what? Whatever.
Contact.
The link to join the WhatsApp group.
Okay. Teacher Charles, do you have you here on call? Okay, friends.
Teacher, cut to work on our WhatsApp.
As per our WhatsApp groups, let me look out. Teacher Doreen.
Yes,
Teacher Doreen, are you able to access the links? To senior,
Let me check here in a minute.
Senior 2 and Senior 3. Please post them here as I attend to a few hands here. Okay, Joy, do you want to say something?
Teacher. So, teacher, I kept on getting disturbed due to network. Where do you think I can get the solutions and the questions at the same time?
Okay, we are going to arrange and post the recordings in our WhatsApp groups. Okay, And as well, we posted there the procedures, so you can find them all there. And then I will say that we can as well use the FATE lab to experiment a number of experiments there, so they will guide you through in that sense.
Teacher,
So
please
Joy,
send a link. Teacher, send a link
okay,
for FATE lab to the group.
Okay, FATE lab. Let me share that here as well. Let me run through. Okay, FATE lab.
This one.
Okay, as I'm getting the link, let me attend to other questions. Anyone with more questions? You can unmute and ask.
Excuse me, sir.
Yes, please.
When we're finding the t-squared, is it just okay if we just get the answer for the period, then just square it and get the number in 4 significant figures?
Yes, as we said, as we obtained small t, the time for 20 oscillations, okay, it helps us obtain capital T, which is our period, okay?
Yes.
So for each, you obtain the period, the corresponding period from 100 meters to 50, okay?
Okay.
And then the values we have obtained for T, that is capital, will help you obtain capital T
squared.
Okay? So you just square, yes, you just square the values. Okay?
Then get the answer in
just square
4
the values.
significant figures.
Yes. And we say that the significant figures will determine the number of decimal places to write in that case. Okay?
Okay, thank you.
All right. So for those of you who wanted the FATE lab, the FATE lab link, you can download it there on your laptop. It is easier that way, and you can access it offline. Okay, but if you use the link we have in the practical procedures, then you will access that online, as Mr. Paras said there. But if you want to download it, please make sure you have a stable network and you're able to sacrifice about 499 MBs. But it will be of importance to have it as well. Benjamin, lastly, as we close this. Okay, Benjamin has lowered his hand. Okay. Friends, I don't think we can exceed this. Thank you for coming. We meet next week during our lessons at 2. And if you have any concerns, please, you can reach us through our subgroups and the Padlets as well. And we shall be glad to look at your work. We shall be glad to look at your work. Basically, the results for this practical. Thank you for coming. I wish you a blessed weekend and God bless you.
Thank you, teacher.
Bye, everyone. Bye. Thank you, teacher. Bye, Priscilla. Bye.
Bye, teacher.
Bye.
Bye, everyone. Bye, Priscilla.
Bye. Have a
Bye,
nice
Mama.
day, teacher.
Bye, Dad.
Bye-bye.
Bye.
Bye,
Okay.
Katie. Bye, Daddy. Bye.
Meet you again.
Bye, Kara.
Vivian.
Hey, teacher.
Bye, McLean.
Bye. Bye, Daphne.
Bye. Who's that, by the way?
Daphne, what was them?
Ah?
Bye,
teacher. Yes. Bye, Vivian. Bye, Maria.
Bye.
Bye, Vienna.
Bye.
Bye, Daphne.
Bye.
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 Some of you are saying bye, but you're not even leaving.
Stay together. I want to call you.
You're not alone. You're a new person.
It's hard to say bye. Aha. It's a weekend.
When did you party?
I know.
Hey.
By the way, Kelly, where are we going this weekend?
Eh?
Where are we going?
Anyway, I just mentioned me, I'm doing the bills, like, you know, my stuff, eh?
Yeah,
How much is so sad?
Just mention.
Where are we going?
You're done. Just mentioned you pay.
I'll pay.
Guys, how are you?
Teacher, should I close the meeting?
No.
No.
Not yet.
Because I can hear people have weekend deals now. Weekend deals.
We're still planning. Still planning the party.
Sir, don't close.
Teacher, please wait. Let us finalize.
Hey guys.
26.
Albert, hi.
So what's up?
Nothing.
Yeah.
Jonas.
No.
Hello guys, bye. Wednesday.
Wait.
Bye.
Bye.
Don't go just yet.
Lisa, what do you want?
I don't know, what do you want? Guys, bye. I'm gone.
Bye.
I'll see you
Bye.
next
Bye.
Bye. Kelly, did you attend the lessons from Monday to Friday at 2?
That is a good question. Did you attend the lessons from Monday to Friday?
Teacher, are they WhatsApp lessons or Zoom lessons?
From 2 to 4?
Me, I've never attended.
Which lessons?
I've never
attended. What is the problem?
Tell me your number.
I may fail to log in.
Kelly, do you?
You don't log in into Zoom because you have logged in now. You've logged in Zoom. How come you don't log in?
No, teacher, I'm talking about the e-learning platform.
Have you registered today?
No.
Did they give you a registration? Teacher Jose,
No.
can you pick that registration? Okay, are you in the WhatsApp group?
Yes,
Have you seen that urgent registration?
I haven't.
Okay, we are going to post it. We are going to post it. When you register, then we shall enroll you in the e-learning platform because you are going to miss next week a number of things.
Okay, teacher.
So don't make the WhatsApp groups noisy, just make them more academic so that you follow the information that we direct you to.
Okay.
But 2 to 4, there is always a lesson on Zoom. So don't miss those lessons. They are always posted in the WhatsApp group.
Every day?
Monday to Friday, 2 to 4.
Hey.
Hey.
Okay.
So I'm going to close this meeting because another class is coming in now, okay? Bye.
Bye.